and FET show this really nicely. I would suggest that if you have a hard time figuring out how this stuff works, play around with it. Like, check to see that it makes sense to you how that blue one and that orange one add up to the black one. There are some people that really struggle with like what I mean by the slices. Really add up the slices one slice at a time. We've got these nice stacked graphs. We should be able to figure this one out. Now, the only thing that I would say that I don't like about this is that it doesn't allow you to vary the widths of the functions. So that has to stay the same width as each other. That's okay with me too, but you do get a bunch of weird things. There's going to be some homework questions that have shapes like this where you're trying to add them up. If you're able to reconstruct any of those shapes in this interactive, then you're welcome to. But really and truly, you're meant to be able to draw the slices yourself and do the addition yourself. Okay, I know this kind of does it for you. So treat it as kind of like a helper for you to get your head into the game. Don't treat it as something that's going to do the homework for you, okay? Let's take a look at the next bit. All right, we'll get this one out of the way. And I'm going to do a little bit of a sidestep on this. I want to talk about, I showed you folks in person standing waves. And so I know it seems like a little bit like it's off topic because we were just talking about superposition, but standing waves are actually formed because you send a pulse one way along the medium, it reflects back off the end of that medium, and then the transmitted pulse and the reflected pulse interfere with one another, and it really is superposition. It's one wave interfering with another. But it's just caused by the same person initially, right? So we have these idea of standing waves, and when I look at standing waves, there's actually some vocabulary associated with standing waves. One thing that we talk about is nodes. And so I'm going to draw in black where the nodes are on this standing wave. So this is a standing wave that's wiggling up and down, and it has 5 nodes. I'll label them as N. There's also a thing called an antinode. And nodes are where destructive interference happens. Now, this particular diagram has 1, 2, 3, 4, 5 nodes. An antinode is where the constructive interference happens. In other words, it's where the maximum motion happens on a standing wave. So these guys here would be my antinodes. And like so many things with waves, you got to remember that this is a schematic diagram and it looks like it's just like fixed in place, but this is a wiggling wave. And it's just showing the 2 extreme positions that the antinodes can take for a standing wave.
Would it be on the bottom as well, or just the top?
What's that?
Would it also be on the bottom or the top?
It's on the top and the bottom.
So it kind of just 4 8.
Well, yeah, so that's a good point. There are only 4 antinodes here.
Okay.
So let's see. The number of nodes in a standing wave shown in the diagram below. We're talking about this one here. How many antinodes would be in this diagram? Count it out. Yeah.
Why are the waves canceling out?
Why? Well, you know what? Why are they canceling out? That's a good point. Let me bring this over, okay? Let's do this as a simulation just so we can see what these pictures mean, because I think that can sometimes be a trouble. So this one right here, this is a standing wave that has 2 antinodes, okay? And you notice that for a moment, it does lie flat, canceling out, I guess, but it's always oscillating back and forth, antinode, antinode, antinode. Right where my pointer is right now, there's an antinode, and right where my pointer is right now, there's an antinode, and where my pointer is right now, can you see that there's a fixed point? That's a node. So this would be a situation that has 3 nodes. Now, if I take it up to, there we go. Oh, that's, maybe I want to be on this one. No, that's unfixed ended. Actually, we were talking about fixed ends versus unfixed ends. You see that I have unfixed ends here? let's stick with fixed ends for now. How many antinodes do I have now?
3,
3. How many nodes do I have now?
4.
4. Yeah. So I think we get this idea. What's also being shown in this illustration simultaneously is alternating densities if this was a sound wave. So maybe the green lines are a little bit distracting in that way, but that's what the green lines are meant to be showing, is these oscillations of densities as well. So we'll just kind of leave this for now. I don't know, does that answer the question though?
Yeah. How would that be in real life though?
If this was in real life, we're going to play around with slinkies and we should be able to hit this exact same thing. If you were playing with a guitar string, then you'd be talking about holding your finger at different frets, and there might be a fret right here where my finger is right now, or there might be a fret right here where my finger is right now, and that would constrict the length that the string could vibrate. Right? It would basically alternate where the fixed points could be on your string. Right? In terms of open-ended, we'll get into it later, but for the open-ended oscillations, we're talking about like wind instruments where there's actually literally open ends for the air to vibrate. I think we're still kind of like in a mode where we're thinking about vibrating strings, though, because I think for a lot of us, it's easier to think about fixed-ended strings than it is to think about open-ended air vibrating. But we'll get there. Don't worry about it. All right. So with all that in mind, how many nodes are there in this picture?
8.
8. Is that what I heard? Yeah. Looks like it. How many antinodes?
7.
7. Now, it seems to me, and actually I could bring my animation back over again, it seems to me that the number of antinodes is always going to be what? 1 more or 1 less than the number of nodes?
Plus.
1 less. Look, I got 3 antinodes here and 4 nodes. I bet you if I went over to the second harmonic, I've got 2 antinodes and 3 nodes. For these vibrating strings, I seem to always have 1 more antinode, or 1 more node than antinode. Pull that back over. All right, so number of nodes in this pattern. If you're on video, pause it and zoom in.
9.
9. Yeah. And then of all the labeled points in this pattern, destructive interference occurs where? Where's the destructive interference happening? Somebody with a hand, come on. Yeah? It is A, yeah, B, C, and D. Yeah, locations B, C, and D. Those guys are all destructive interference because destructive interference means nodes. Now, for a single plucked guitar string, we'd be talking about a single guitar string. When you pluck it, it oscillates back and forth, wom, 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 where the string goes from one extreme position to the other extreme position. You can imagine we just plucked this thing. You get an antinode, you get a node on either end, and this thing is like vibrating back and forth, right? If I was going to see that in animation, it would look like this. Oh, this isn't that. First harmonic looks like that. So this is our animation of exactly what we've got drawn on our page right now. Again, just to give like an animation to what's going on, because I hate that we have static paper, but it's what we've got, right? So then when we look at this, hopefully that makes these pictures make sense, because these are actual strings that somebody's been able to capture using a stroboscopic camera. They've got these strings, and if I was going to measure these strings out, look, from here to here would be the length of the string. Agreed? But if I run a piece of whiteout along here, from here to here, is that a whole wavelength? What is it? Half wavelength. That's lambda over 2. How many half wavelengths fit into this? Yeah? 4. Yeah. So let's just say, imagine if the length of this string was 8.0 meters. Let's play the what if. If the length of the string is 8 meters long, how long is a half wavelength? What's that? No, a half wavelength isn't 4 meters. Yeah, 2 meters. Yeah, look at this. That means I've got 4 length divided by 4 equals lambda over 2. You guys see that? Because there's 4 of them. And then I say, okay, well, wait a minute. Couldn't I just write this as length divided by 2 equals lambda? Seems to me. What we're saying is that's lambda. What about this one here? What if it had been the same length of string, but there was 3? In other words, hey, by the way, when I talk about there being 3 here, people talk about loops. There are 3 loops. This guy here has 4 loops. That's a way of talking about this. This one is 3 loops. How many loops on this one?
2.
2 loops on this one. How many loops on this one? 1 loop, right? So I say, okay, there's 3 loops. The length is still 8 meters. Remember, this is lambda over 2. Can you guys beat me to it? Can you calculate what a wavelength is? Calculate lambda.
2.67.
So I take the length divided by 3. Length divided by 3 is going to be equal to lambda divided by 2. Three lambda over 2. Or I can write it as 2/3 L equals lambda. And what somebody showed it out already was lambda is equal to 2/3 times 8.0 meters. So what's the wavelength end up being? 2.67?
No, that's 1/3. That's 1/3. It's 5 point.
Oh,
5.3.
somebody with a calculator, help me out. 5.3 repeated?
Yeah.
Yep. Meters. All right. You know, I would really love to have a formula for this because it seems like I don't like having to think this through over and over again. So I want to pick on this one, and I think I'd like to. You know what? Maybe I'd like to rewrite this one. This one was L equals 4 lambda over 2. Maybe I want to pick on this one. You notice that the 3 has to do with how many loops there are, and the 4 has to do with how many loops there are. So I think that the equation I'd like to come up with is the length of the string is equal to the number of loops times lambda over 2. That seems reasonable. And you can test this out for any one of these loop diagrams to check to see that it's going to make sense. That means that I should be able to figure out what the wavelength is if I know how many loops there are and how long my string is. That's kind of by inspection. I won't even call that a derivation. That's just some good, honest thinking, you know?